Primeiro queria agradecer do IMPA por convite e também agradecer do professor Camacho, que me ensinou muitas coisas. E mesmo eu estar muito longe, ainda está continuando ensinando. What I want to talk today, the origin comes from real differential equations and Hilbert 16 problem on the number of limit cycles. But I'm going to start with an abstract context. At first, it has nothing to do with the Hilbert 16 problem. So, so we have the projective line. I name it P1. This is the union of C and infinity. We have a divisor in the projective line. With the mi positives. And we have a V, a vector bundle of rank alpha on P1. So let us fix the notation. So I will use this. I will denote C1 with until CR by the set C. And the last object which we are going to deal with is this object, which I explain what is this. OP1 and V. Here, by V I mean the sheaf of holomorphic section of the V. I denote the same by the same letter V. And this is the sheaf of one forms on P1 with poles in C, such that the multiplicity of the pole is less than mi. And this product is taken over OP1. And really, it is not necessary to understand this notation. I will say the geometric meaning of this object. And what satisfies this nabla is the Leibniz rule. I write here. df omega plus f omega. And yeah, here f is the holomorphic function and defined on some domain U in P1, and omega is a section of V in U. But what kind of geometric objects, geometric interpretation this object has? We have a P1 here. So we have this C1 and then C other points, C2, C3. We take a point P. We look at the fiber V here, VB here. And we take a fixed point in VB. We name it E. there exists a unique section of V passing through E. Let us name it let E0, E. There is a unique section, E, section of V in a neighborhood of B, such that, let us name it E, such that nabla E is equal to 0 and E at the point B is E0. So the situation is something like in the previous, in the talk of yesterday of Professor Gomez meant that now we see the similarity more. So, for example, let us again take this fiber VB and take C1 here. We take a path starting from B and turning around C1 and going back to B. Then we have this section of V. We can this section can continue holomorphically along this path. And then it returns and cut the fiber VB in another point. So what we obtain is this map P1, map T from P1 the homotopy group of P1 minus C to the linear group of VB. And this is the monodromy group. Monodromy representation of this connection nabla. You will see that when I will say the origin of this problem, you will see that really this notation is better than the, for example, looking this object as a or holomorphic relation or as Riccati equations, because the origin is completely different from the Riccati equations. Okay. When we have a connection like this in nabla, in the dual also there is a connection. There is a connection in the dualist space. I denoted it with a star with the same divisor. We started the dual of is the dual of V. And the definition of this connection is in a natural way. When we have a delta is a section of, if delta is a section of V star in some open set, then nabla ester delta and acted on omega. Omega is a section of V in the same open set, will be defined in this way. Differential of delta omega minus this one. And this is the pairing, just the vector bundle with his dual. These objects are linear functions from this object, so we can form this pairing. And yeah. Okay. And now, what is the problem? We are interested with this this object. I suppose that, for example, let us suppose that delta omega are defined in the U and open set OU in P1. And delta is just I forgot to say that these are called flat sections. Delta is a flat section of V star, and omega is a global meromorphic section of V. So now what is the problem? Describing the maximum multiplicity of delta omega. Of course, in terms of our data of the connection, and also the number of poles, the pole order of omega, because omega is a global section of V, meromorphic section. So we must put some restriction on the pole orders, and we are interested to describing this maximum multiplicity, these kind of functions. And now, to get similar to the notion of abelian integral in differential equation, I am going to write this expression like this. So I'm going to write this pairing as integral of omega. This is just notation, but it is going to be near the origin of the problem. Okay. To see more similarity of when I no. Just in this formula, when delta is flat, this means that this part is going to this one is going to be 0. Okay, so in this formula, when the delta is flat and we use this notation, what we obtain is this one. I'm going to write first this one. The integral over delta is going to be just something I forgot to do, that before this one, when you have something like this, we can take the we can introduce an operator from the global sections of V to the global sections of this sheaf. So what we obtain, I'm going to denote it again with nabla, H0, P1, global section of V with poles at infinity, with arbitrary poles at infinity, 2 H0 global sections of V, of course, with poles in D and with arbitrary pole along the infinity. How we obtain this, this operator? We take a global section here, we look at its image here, and then with the vector field d over dt, we cancel this part. So again, we obtain global sections of V. Of course, there are some poles on which appears from this part on the image, and we have already poles along the infinity. So this sheaf theoretically map gives us this global map. Now this one, according to this equality, satisfies this delta omega is equal to, we act, the vector field d over dt acts in this term, so we obtain differentiation with respect to t of delta t minus this one. And what I wanted to say just a couple of minutes before was that when delta is flat, then this part is going to be 0 because this one is 0, and we are going to obtain this formula. And we use also this notation of omega over delta is going to be nabla omega over delta. And the people who knows a little bit in the real differential equations now, really they see that the origin of this problem. Now, so now it is time to a little bit explain the origin of this plan with the similarities that we have already obtained. Okay. So let us take the Hamiltonian polynomial, and we take it looks like let us in many cases it has orbits like this, and we take a family of cycles let us take a transverse section also, sigma. And this family of cycles are parameterized by the time, by t in sigma. Let us Okay. So what we can do is to form this integral. Now omega now is polynomial one form in R2, of course real, and so we can form this integral of the polynomial 1 for omega over these cycles in the real plane. And we obtain a function, we name it h at t. These functions in differential equations, in real differential equations, are called abelian integrals. And why they are important? And why these integrals are important comes from the perturbation of the differential equations of the Hamiltonian equation dH by let us say by the one form omega, which we wrote there. Oh yeah. So, and more terms. So, let us first take. We have an original cycle. We fix, for example, the one value t0. Okay. So, and now we are interested in the number of limit cycles which can appear around this cycle after this perturbation. And this number is controlled exactly by ht. Why? Because when we write let's write here epsilon. This is t plus epsilon ht plus higher epsilon 2 higher terms. So we had our sigma. So we have a perturbed holonomy or Poincare first return map, the deformed one, the perturbed one, and we can write the Taylor series. And when we write Taylor series with respect to the deformation parameter, this ht, these integrals appear as a coefficient of epsilon. So of course it is easy to see that now the zero, the multiplicity of ht in t0 represent the number of fixed point of h epsilon t, and the fixed point of h epsilon t are exactly the number of limit cycles. Okay. And so, how we see this abstracting with this real integral, the relation? In fact, we must to do that one. We must know that H is topologically trivial logically trivial over P1, a finite set. This finite set usually always contains the set, the critical values of what?
No, H is
yeah, I explained the H in the case of polynomial, just in simplest case. Let us write here C. This critical points are here, but there may be another points of C which are not critical point of the polynomial H, but they may appear also in this finite set. So it is topologically trivial. So we can take this vector bundle H1 of the fibers. That's 2H. H1T complex numbers. The union of the cohomologies over T. Let us say name this one B. T over B. This is going to be a vector bundle over B. And here it leaves a very natural connection, and which in this vector bundle, the flat sections are exactly the elements of the cohomology with rational. The elements of a flat section of this vector bundle with respect to the canonical meromorphic connection is going to be exactly the elements of the monodromy. So let's say, when you look at in the homological case, just I remember that here is already complexified. Yes, so we are considering the fiber that complexified space. So these cycles which are obtained by monodromy are going to be a section of the homological vector bundle, and this section is going to be the flat section. And one can extend this section, this meromorphic connection, which is defined over B and is holomorphic over B, to a meromorphic connection on the whole P1. And this kind of theorems is not done exactly for Hamiltonian ones, but for Lifshitz pencils. And because each kind of critical fiber needs special treatment. Okay. And in this case, exactly, this integral is going to be this integral which we are studying. So we are going to state our theorem for this abstract cases which we obtained by by meromorphic connections. Okay. Just a definition. Now, remember that we defined the representation of monodromy in GLVB. We say that nabla is irreducible if the action of the homotopy group on a single element of VB generates the whole space VB. So what we do is that we take VB and we take a point E0, and we do the monodromies, all the possible monodromies, and we obtain E0, E1, and so on. And the notion of irreducibility says that all these elements generate the space VB. And when delta is irreducible, let us say the main theorem. Also before, just another definition. We take an element in this a global section with poles at infinity, and we let also poles at arbitrary poles in C. Let us define degree of omega, the sum of pole orders, and I define how H delta n, the maximum, the minimum number, are such that for all omega with degree of omega less than n, these vectors, these global sections, we can now iterate minus 1 omega generates each fiber VB. B belongs to this P1 minus this finite set. Just a remark. When omega is when nabla is irreducible, then there it's just then omega, nabla omega until nabla alpha minus 1 omega. Here alpha is the rank of the vector bundle, rank of the vector bundle V. When nabla is irreducible, at least we need this number of elements, because the rank of the each fiber is alpha, so at least we must do this number of iterations. And when nabla is irreducible, it is not difficult to see that these elements generates the fiber VB for B generic ones. And now the main problem is that this, in this case, the generic one we can produce with alpha, these alpha elements. But to produce all the, in all points B, in all points B outside C, now we are going to give a upper bound, which is this upper bound is going to be written in terms of our data. So our theorem, it has first part. First of all, that this H nabla n is going to be to less than an expression like this, alpha minus 1 sigma mi plus alpha n plus 1 minus alpha alpha plus chain class of V. And here, again, remember, alpha is the rank of the vector bundle. These are the multiplicities associated to the point C, which our connection is defined. N is the, we are working with this global sections, and the chain class of C, V, is the sum of chain class of the line bundles LE, where V, according to Birchhoff or Grothendieck theorem, is written as it's the decomposition of the line bundles. And this, the second part, also is going to be this one. That's the H supremum of delta n delta. What is this one? Are exactly the maximum multiplicities of such an integral over our flat section delta, and with omega varying in this domain. Just a little bit about the previous works about this kind of things. In the case of Hamiltonian, with generic hypothesis on the critical points of H and also on the image of H, this kind of result is obtained by Mardesic in 90, but in some sense this one generalized his result and also shows that the essence of the proof there is very simple, because we are going to use just some manipulations of the pole order of a global section of a vector bundle and counting the poles and saying something about the number of zeros. Just another remark about this one. If somebody wants to know more about the history of this problem, Ilyashenko has written an article in Bulletin of American Mathematical Society, 2001 or 2002, which he explains all the problem, all kinds of problem which the people are working with respect to these abelian integrals in real differential equations, of course. Before going to see how the proof works, I open a parenthesis that really I enjoyed also doing this complexification. But something I learned, that when you complexify some real object, you must never forget the real structure. I mean that you can do a lot of things with complexifying, but really forgetting that your structure was a real structure, you lose many things. And so, for this reason, I think that this upper bound is very big. And because, for example, in the Mardesic case, it is going to be something polynomial of order 4 in the variable n, which n is the degree of the Hamiltonian polynomial, and also the degree of these polynomials, these polynomial one forms. Of course, for the Even for the global case, for the Hilbert-16 problem, we wait for a very smaller numbers, and just around the trivial cycle, getting this number of a limit cycle seems to be impossible. Okay. And how the proof works? So what we do, let's first look at the first part. What we do, we look at this element. Omega, nabla omega, which with alpha minus 1 omega. This is going to be a global section of the determinant line bundle V alpha, which is the wet product of the elements of V alpha times. This is going to be line bundle. And what more? And the chain class of V is going to be exactly the determinant of V. The chain class of V is going to be exactly the chain class of this determinant. Now, so we have a global section of a line bundle. First of all, we must observe that I is not identically 0. And why? Because, so to prove this one, we take omega, which with nabla omega, and until nabla k omega. This one suppose that is not identically 0, and let us say this one ak. And let us suppose that AK, which with nabla k plus 1 omega is identically 0. So here is our P1, VB. We form the vector spaces generated by these elements, omega and we print the bundle over now it is going to be P1 minus C union with infinity and also union with zeros of RK. And how it is defined with Vprint generated by omega nabla omega nabla k minus 1 omega And so we obtain a subvector space V'prime. And now, this hypothesis that nabla k plus 1 omega belongs, a wedge with this one is 0, means that this one belongs to the space generated by these elements. And this means that nabla induces a new connection on V'prime. And now if it means that the monodromy representation preserves V'prime, it sends the V'prime to itself, but this is a contradiction with our hypothesis of irreducibility if V'prime is not the whole V. So this AK is not identically 0. Now, what we must to do exactly now to look at the pole order of omega, and just we must count where are the pole orders, where we have pole for A, and then the sum all of them, and then say and then find an upper bound for the 0 of the vector field A, and the 0 to find an upper bound for the multiplicity of a 0 for A, and this is going to be exactly this upper bound. So when we do this one, that's the, oops. Then let us, for example, the pole order of omega at infinity, if it is m, when then the sum of pole orders at the points of C is going to be less than alpha minus 1, this sum alpha n minus m. And this is just by counting the pole orders here in each term. And we must look for the infinity separately. We must observe that there is a vector field with 0 of multiplicity 2 at infinity. And considering this fact, we obtain this, that the pole order of omega at infinity is less than this sum, m plus n minus 1 plus m minus alpha minus 1. And then when we take the sum, and then considering that our A is a holomorphic section, as a meromorphic section of the determinant Lie bundle, then the sum is going to be this one, and that we are working in the determinant bundle of V, then we obtain this number. So this to obtain this upper bound is going to be not a very difficult thing. Okay. Just a last remark. Georg-August-Universtaet remark this abstract case also. For all omega, a global section and a flat section, these are satisfies these function satisfies linear differential equations, and the monodromy of this differential equation is going to be the same, the monodromy of the connection. And even more, if we have a differential equation which has the same monodromy of the connection, then we can find a global section of omega of the V, and the flat sections that the given linear differential equation is represented by our connection. And also the concluding remark that these linear differential equations may have also more singularities than C. The linear differential equation, they have singularity on C, and may have singularities in other points which are called apparent singularities. Okay, I finish.
Any question?